here's some practice with predicting the products of addition reactions. And there's a couple of points we want to remember when we're faced with problems like this. First, we need to identify it as an addition product, of course, but then the question is, what is being added across the double bond? And the second question is, what do we expect the regioselectivity to be? And of course that means, is it Markovnikov or is it anti-Markovnikov in terms of the addition? Or is it neither? It's possible that we're adding the same thing to both sides of the alkene, and therefore we don't have, for instance, the OH adding to the more substituted side. And also then the stereospecificity. Can't spell today. Stereospecificity. Does it add syn or anti, or is it neither? Okay, so let's look at these 6 examples here. These are all addition problems. Towards the end of the chapter, we'll get into more just random predict the product type questions, but here we have all addition. So what is being added to the first one here? We're adding hydrogen, so there's going to be an H on both sides of the double bond. And we're going to create a new stereocenter right here, because it's going to have 4 different groups. And we know that we don't create a stereocenter on the first carbon because it already has a hydrogen. If I add a second hydrogen, I'm just creating a CH2. So I'm going to go ahead and draw 2 enantiomers. And that's with the H added to the back side. And then I have, of course, the other version, the H added to the front. You'll notice I didn't draw the H because I don't need to. I could, but in this case I'm not going to. Second question. Same alkene, we're adding water though. This is an acid-catalyzed hydration, and so it's going to add regioselectively, it's going to add the OH to the more substituted carbon and the H to the less substituted carbon. So I'm going to make one new stereocenter here. It's going to look very similar to what I just had, except now I have an OH. And I'm going to draw the other enantiomer as well. So I've made a pair of enantiomers here. The third question, we're adding Br and Br across the alkene. So we're putting a Br on both sides. That makes it a little easier. And we know that the stereospecificity here is such that the bromine is added anti. So if I have the bromine down on the top carbon, I need to have it coming up on the bottom carbon, and vice versa. So I'm going to make 2 enantiomers again. So you see how it's a very good idea to have a good grasp of the mechanism for all of these so that we can quickly come up with the regioselectivity and the stereospecificity. Here we're adding bromine in the presence of water, so we're going to end up with a OH on one side and bromine on the other. And we know that the OH adds to the more substituted carbon. Again, it's anti-addition. So I have that version, and then I'm going to have the enantiomer as well. It's called a hydrohalogenation. So again, I've created 2 enantiomers here. So we'll call this number 5 up here. This is hydroboration, so we're adding H and OH, and we're adding syn. And so I'm going to put the OH on the less substituted carbon. You'll notice there's a stereocenter already in existence, so I need to keep that in mind as I draw products. Really, I just need to observe that it's there and not change it while I'm drawing the products. And let's say I want to put my OH on the bottom. The H also needs to go on the bottom because, again, it's syn addition, and that means that the methyl is put up in a wedge. Then I need to add the H and the OH from the top face as well. And here you'll see that I've made a set of diastereomers, and that's because of the existing stereocenter that's unaffected by the reaction. I have a set of diastereomers as my product mixture, and they are syn addition of the H and the OH. And lastly, I have a alkoxymercuration. So I'm using mercury to add normally water, but in this case we've added ethanol, and that's our nucleophile. So we're going to add H and we're going to add OET on either side of this alkene. And we know that alkoxymercuration adds our nucleophile, the OET in this case, to the more substituted carbon. So I'm going to draw that like this. And then in this case, it looks like we did not form a stereocenter, because my H, of course, gets added there. There's another H there already, so that's not a stereocenter. This carbon is not a stereocenter because it has 3 carbon groups on either side of it. So this would be the only product I need to draw. The tricky part of this question is understanding that ethanol is the nucleophile and not water like we're used to seeing with hydroxymercuration. This is alkoxymercuration, and it really just depends on what the nucleophile is. That should be easy to observe as long as you're careful in your evaluation of the starting material and the alkene that we're adding.